Hi dear students, today we are going to study about electromagnetic induction. Electromagnetic induction is being taught as a chapter in Ncert textbook as chapter 7 of physics part 1. So the concept of electromagnetic induction is not a new one. The concept of electromagnetic induction dates back to 18th and 19th century. The two pioneers who worked on the concept and on the idea of electromagnetic induction were Joseph Henry and Michael Faraday. These two scientists in the 19th century worked tremendously on the concept of the electromagnetic induction and discovered the principle behind generating electricity from magnetism. They independently performed experiments which demonstrated that when a conductor coil placed in the presence of a time varying electromagnetic field or magnetic field generated an EMF within it that induced current inside the coil. Now let us look into the idea or the concept of electromagnetic induction. Without the discovery of electromagnetic induction, many advanced instruments that we use today, such as microphone, telephone, transformers, and mainly the electric generators, wouldn't have been possible. All these instruments make use of the basic concept of electromagnetic induction. Before moving on to the applications such as these, let us look into the concept of electromagnetic induction using the various experiments performed by Henry and Faraday back during their days. The experiments performed by Faraday and Henry can be capsuled into three different analyses which could be used to understand the concept of electromagnetic induction. Let us see how this works. Experiment number 1. To understand the experiment number 1, we need to set up a system of two coils placed close to each other. Or instead of using two coils, we can go ahead and make use of one coil or a solenoid. So for our case, we may go ahead and you make use of a solenoid instead of a coil. So now we here have a solenoid wounded around, say, n number of times. Say n number of times is the number of turns on this entire coil or the solenoid, and let L capital be the length of this solenoid. let us put these two terminals of the solenoid connected to a device called the galvanometer. Okay, so the galvanometer does is detects any presence of tiny current within the circuit consisted by it. So if the galvanometer deflects, then it implies that there is a coil through the circuit which passes through the coil. Very close to the solenoid that we have just set up, let us place a bar magnet. Now let us move the given magnet from its position to another position very fast, say like that. When we do that, when we move our magnet from say here to over here, what happens is that the number of magnetic field lines that passes through these coils changes, or the magnetic field inside this coil has changed. The observation made by Henry and Faraday was that we see a deflection either right or left depending on which pole of the magnet that you are bringing away from the given solenoid. The galvanometer deflects in that particular direction. A deflection of galvanometer indicates that there is a presence of a non-zero current inside the coil. Now let us take a look at the same experiment, but this time instead of moving them away from the coil, we move it closer to the coil. In this case also we find that the galvanometer will show a deflection. So if you move from A to B, say, the galvanometer shows a deflection maybe towards the right, and now when you move from B to A, the same pole facing the coil, which is north pole in our case, we get a deflection which is opposite to the initial case where we pull away the magnet from the coil. So students, do remember this point, that the direction of deflection, or which itself indicates the direction in which the current moving, is exactly opposite to one another depending on whether it is moving towards or away from each other. So the conclusion drawn from this experiment is that, or the observation that we make from this experiment is that, when magnetic field changes through a coil, an EMF, for those who guys who don't use the word EMF, I can say a voltage, and in EMF instead of which I can use a voltage, is induced. In the coil. Now let us move on to experiment number 2. In experiment number 2, instead of moving the coil, so let me draw the coil or the solenoid in our case. Suppose you had a coil or the n number of coils, which is the solenoid, like this. And then connected towards a galvanometer again. And then we have the magnet. Instead of moving the coil, instead of moving the magnet towards the coil or away from the coil, we make use of the solenoid or the coil to move towards or away from the magnet. So in this case, I fix the magnet, so which means this magnet is fixed here, whereas the coil is movable now. So you can move the coil either towards the magnet or you can move it away from the magnet. In this case also, it was observed that the galvanometer connected to the coil circuit detects current inside the circuit. So the only thing that was concluded by Henry was that a relative motion between the coil and the magnetic field induces an EMF in the coil. Now let us move on to experiment number 2. In experiment number 2, again we will have a coil or a solenoid. Instead of coil, we can make use of solenoid, which is again connected to a galvanometer. It's again connected to a galvanometer. Excuse me, there is a mistake over here. Yeah, it is actually experiment number 3. Okay. So in experiment number 3, we have not just one coil, but instead we have a setup of 2 solenoids placed close to each other. Instead of moving one coil towards the other, the solenoid 2, which here acts as an electromagnet, is switched on. Switching the solenoid S2 on makes it an electromagnet, thus generating magnetic fields around. The solenoid S1 is also placed in the vicinity of solenoid S2, which means there is an inflow of electromagnetic field, especially magnetic field, through the solenoid S1 when you complete the circuit of the coil S2 using the switch S. As soon as the switch S is turned on, the magnetic field through the solenoid S2 starts increasing. This rise in magnetic field through the first coil S1 this changing value of the magnetic field due to S2 in the region where S1 is kept induces an EMF inside the coil S1 or the circuit S1, circuit that consists S1, which means there is a galvanometer deflection shown over here. From experiment number 3, again we see that, or at least what Faraday confirmed, is that you don't need to change the relative position between two magnets. All you need to do is change the magnetic field through the coil. To do that, to achieve that, performing relative motion between two coils, one with magnetic field and a non-magnetic coil, or a coil which is disconnected from electricity, an EMF is induced when the magnetic field in the second coil changes, that causes a surge of electromagnetic field through the coil S1, thus inducing electricity or an EMF inside that coil. Another point Faraday noticed is that the amount of, or the intensity of EMF induced in the coil not only depends on the change in magnetic field. They noted that the EMF induced within a coil does not remains there forever, but reduces to zero as soon as there is no change in magnetic field, which means if you are moving a coil in front of a bar magnet, and once you stopped it somewhere, there is no relative motion happening and thus no change in magnetic field through the coil, immediately the induced EMF goes to zero. So there must be always a change happening. The thing that Faraday noticed was that the amount or the intensity of the EMF induced proportional to the rate or the fastness or how fast the magnetic field through the coil changes. So 2 points to take away from this section is that magnetic field linked with a coil must change for the EMF to be induced, and also the amount of EMF induced will be proportional to how fast the magnetic field associated with the coil will change. It was noted that when you have a circular coil, or at least any loop which is a loop obviously, which means it goes around at least once, will be called a loop. And if you place any magnetic source close to the coil or the loop, and once you push or pull away the magnet, the external magnetic source, the magnetic field within the coil changes, thus inducing current. So it can also be done in another manner. it can also be done in another manner, where to change the electromagnetic or to change the magnetic field through the coil, one can rotate the loop about such an axis, or even any other axis you want to choose can be used to rotate the coil. Thus, even then, we see that an EMF is induced. An EMF is induced. It is found that the quantity that we need to define is not just the magnetic field that crosses a region, but it's the effective amount of magnetic fields, or the magnetic field line, or the magnetic field intensity that crosses the given loop. So to understand what this quantity is, we name this quantity as magnetic flux, without which we cannot understand the concept of electromagnetic induction. As I said, for the EMF to be induced in a coil, not only just the magnetic field associated with the coil must change, but the orientation and the area within the loop of the coil contributes towards the induced EMF. If you change the orientation of the coil to a certain degree, the area exposed through which the magnetic field passes reduces or increases depending on where you are and what you are doing. So, area of the coil also plays a role in the amount of EMF induced. So, to incorporate both these quantities together, the idea of magnetic flux was introduced. Magnetic flux, just like in the case of electric flux, is a quantity which is defined as the intensity of magnetic field dot the area vector. So, what is the peculiarity of this quantity? This quantity over here has incorporated the area vector and the magnetic field intensity. Now, the quantity magnetic flux itself is a scalar quantity. Magnetic flux is a scalar quantity. The scalar nature of the magnetic flux is due to the fact that the product on the right hand side, as we can see here, is the dot product between the magnetic field and the area vector of the coil. So let us look deeply into the concept of magnetic flux. So the definition of magnetic flux: represented by the symbol phi is equal to B dot A. So this is the mathematical quantity, or at least this is the quantitative thing that we can bring close to reality, which can be used to understand how electromagnetic induction works. So what does phi do? Let us look into this using a diagram. The quantity flux is defined over a surface area enclosed by some loop C. So if that C is the loop, then the quantity magnetic flux is defined within the region enclosed by C. So the shaded region is the region upon which we are going to define the quantity magnetic flux. Now let the shaded surface of the C be a flat surface, which means for any area vector, or at least for any tiny area within the surface, has an area vector which will be parallel to any other elemental area within the same closed loop. So for every tiny area or the elemental area you take within C, the vector which represents the area vector or the area will all be parallel. So this is how you define a flat surface. So all the area vectors, all the elemental area vectors within the closed region C will be parallel to one another. So the arrows in this figure indicate the elemental area vectors and their directions. Now let us see, what if some magnetic source generates magnetic field at some location far away from this surface. Let there be some magnetic source, and that magnetic source be producing magnetic field in the entire region, which means at every point on the surface also there will be a value for magnetic field, and let that magnetic field be represented using a vector so and so. So this is the magnetic field at the point, at the given point P on the surface. This point is the P, and that is the and B is the magnetic field, or let me say let that be B1 be the magnetic field at the point P on the surface, and the area, the tiny elemental area surrounding the point P, be called area dA1. So as you can see, the area vector, the elemental area vector dA1, see here elemental area means a tiny area, a small, infinitesimally small area, for a represents a infinitesimally small area. Okay, so the area vector dA1 and the magnetic field in that tiny area B1 be offset by some angle, say theta or theta1 for the convenience of mathematical manipulations. Okay, if you go on to check other regions, say some other region, let me say take this region and let this be Q, this be Q, the point here, the green point here be Q, and the magnetic field at that point be in this direction. See, it can be at a random direction, we do not know. It is the magnetic field at that point is in fact detected by the source, the magnetic source, whichever the magnetic source is, of which we don't have any information. So it can be any direction, so we can just randomly pick one direction. So, and the intensity be some B2, and the area vector be say some dA2. Okay, and let the area vector and the magnetic field vector be offset by some other angle, say theta 2. Moving on to some other point on the same surface, let this be the point, and I'm going to call it R. Remember, all these points P, Q and R are on the surface C. So we are only analyzing for the magnetic fields that pass through this surface, exactly through the surface. So the magnetic fields are taken on points on this surface, okay. And let the magnetic field at R be say in this direction, and let me call it B3, and let that area vector be called dA3, and the angle between them be some theta 3. So you can now get now you get a point. So as you can keep continuously, if you can keep counting all the elemental areas, and you can go ahead and represent such a magnetic field vector at each point, and you can also represent an area vector surrounding that tiny point, a tiny area surrounding that point. As you keep continuously doing that, you will end up having infinite number of pairs, because we are only taking one point at a time, and in that entire region there are there could be at least infinite number of, a very large number of points, and infinite number of points are there on C. So you will have like a pair such as BI, which could be B1, B2, B3, etc. And also you will have another and the area vector of the pair, which could be DAI on that surface. You can keep counting all the pairs and perform this dot product B dot DAI and perform a sum. Since you are performing a sum not on a countable region but an uncountable region, this summation index should be dropped, and instead we should perform an integration. This gives you the magnetic flux through that entire region. Now how can you, suppose if you wanted to just find the magnetic flux through the point P, what would be the magnetic flux through the point P? So just to analyze that tiny amount of magnetic flux, say d phi at P, it could be done just by performing the dot product B1, because B1 is the magnetic field at P, dot dA1, and that is the tiny infinitesimal area surrounding the point P, which is dA1. And you know how to analyze a dot product. Dot product is analyzed by multiplying the magnitudes of the vectors involved, which is B1 is the magnitude of vector B1 and dA1 is the magnitude of the vector dA1, times cosine of the angle between them, and the angle between these two vectors is theta 1. So this is the product in its entirety. As you can see, magnetic flux incorporates not only the strength of the magnetic field, it also incorporates the area, the effective area exposed in the direction of the magnetic field. So magnetic flux is in fact the product of magnetic field intensity and the effective area in the direction of magnetic field. So it is this quantity, which will be used to understand what the electromagnetic induction is. From various experiments which are not mentioned in our lecture, it has been found that magnetic flux is the quantity that needs to be changed, or that needs to change in order to induce an EMF through the coil which covers the region for EMF to be induced, the magnetic flux associated with the coil must change. So for the case of the coil C, the magnetic flux through the coil C will be this integral sum, or the integral. Actually, we are not supposed to say integral and sum, because integration itself is a sort of sum, a continuous sum of infinite terms. So this entire thing equals the magnetic flux through the closed loop C. And once this quantity changes, there will be an EMF. There will be an EMF that will induce a current along the path C. The direction of the current induced will depend on how the magnetic flux changes. So it can be either clockwise or anti-clockwise along the path. So the induced EMF depends on the flux within the region, how fast the flux changes within the region. If the magnetic flux changes, associated with some coil, some loop C. Suppose we have a metallic loop C, and you plan to find the magnetic you find the magnetic flux associated with this entire coil. All you have to do is sum over all the elementary fluxes. So what is an elementary flux? Elementary flux, magnetic flux, is actually the tiny amount of flux through a tiny region within the coil C. So the magnetic flux, the total magnetic flux through the coil C will be integral sum of all the tiny fluxes on the surface. And what is the tiny elementary or at least we could say elementary flux through this coil? It could be some tiny region having area vector dA, and the magnetic field at that point, say B, and the value of the magnetic field depends on the point where we are analyzing it. So it can be different for different points. So it might not be the same over here it might be different, and the orientation itself might differ. But anyhow, for this tiny region, the tiny magnetic flux is B dot dA, putting them within the integration, we get integral B dot dA. So this is one of the most general ways to find out the magnetic flux associated with a coil enclosing a region. So we do not have to care about any magnetic flux outside the region. We only care about magnetic flux within the region. The evaluation of total magnetic flux within the region enclosed by the coil C or the loop C can be made easy. That can be done if we come to a region where magnetic field B is a constant vector. Also, if this quantity is constant, the integration becomes more simpler, and also the area enclosed by the coil should have a regular shape such that the total area can be evaluated using known formulas. So if these two things, one is the B vector to be constant and the other one is that the area has a regular shape, area has a regular shape means the C must be some loop which looks like a square or a circle or even an oval, or not an oval but an ellipse, or any other regular shapes such as pentagon, hexagon, etc. If the area has such a shape and the B is constant, then evaluation of this total integral or the total magnetic flux would become simpler. But that need not be the case. A loop can be of any shape, the area enclosed could have any size, the magnetic field need not be constant. In such situation, evaluating the integral would be the only remaining choice. As an example, let us evaluate a simple case where the magnetic field is constant. Let us evaluate the magnetic flux where magnetic field B is a constant. A constant magnetic field in a region indicates a uniform field. So the peculiarity of uniform field is that all the magnetic field vectors will be parallel and will have the same magnitude, somewhat like this. So since it's within a region, I will have to draw it, extend it to other area also. So on and on. Let us imagine a coil, which will enclose some part of this area. So that coil, let the shape of the coil be a square, and I know that does not looks like anyhow close to a square, but let me just use a regular shape maker. Yeah, okay. So in this region, okay, I think this figure looks a bit complicated, so let me redraw it. Okay, so let me draw the area first. Okay, let this be the area. So see, we have assumed a coil C, which looks like a rectangle having length L and breadth say B. So this is our coil, and the magnetic field let there be some magnetic field crossing this region. So I'm going to draw a uniform field, and the coil C is placed in a region of uniform field. Okay, so uniform field means all the magnetic field vectors will be parallel to each other at every point. At every point, I'm only drawing for magnetic field at various points, just to indicate that the magnetic field exists everywhere. That's all. Alright, so that is the orientation of the magnetic field. Now what about the area vector on this loop? Since that is a rectangle, the surface area inside the rectangle will be flat, which means every point will have an area vector which is also parallel to each other, So area vectors represented using the black arrow at all points, at several points, are also parallel to one another. So this is the area here, area vector here, this is the area vector here, this is the area vector here, and over here too, so on and on. Since it's a uniform magnetic field, all the magnetic fields can be called vector B, and so on. Suppose which means this entire region has area vector dA and the magnetic field B offset by the same amount, which means the angle between these two vectors is same in all the pairs. So you don't have to go ahead and analyze the tiny flux d phi in each cases, but instead you can write d phi is just B dot dA, where when you expand the dot product it looks like B dA cos theta, where theta is the common angle, the angle which is between this pair of vectors, and that is same for all pairs. So you can just represent that angle using theta. Okay. Alright, so now we need to evaluate the total flux through this region. So how would we do that? For that, we perform the integration. So the total flux phi through within the coil C is equal to integral B dot dA. So this was our general formula. We have come to expand the dot product, and we found that it is B dA cos theta. Before performing this integration, we know the fact that B is a constant and theta is a constant also, because we have the same angle throughout. So these two quantities can be taken out of the integration, and we get B cos theta integral dA. Now we integrate over the entire area, which means we are adding all the tiny areas within the region C, within the region enclosed by C. What would it give? It would give the entire area of the loop C. So let that area be A. So A is the, so after doing the integration of tiny areas, you get the entire area within the region enclosed by C, which is which would look like, which would be this, not that, I'm sorry, which would be this, yeah, which would be this green area represented by this green shaded region. Let that area be A, and we have outside B cos theta A, which means which will culminate to look like B A cos theta, and B A cos theta is in fact the dot product B dot A. That means the entire region the entire region enclosed by C can be represented using, so suppose this, let me give you a side view of the coil C. So this is our coil C, and that is the green region, that is the region. This over here is the region that we were talking about. That means the entire region, flat surface C, flat surface enclosed by C, can be represented by a single vector A, and the entire magnetic field, instead of using entire magnetic field at every point, you can just assume a single magnetic field in that region, and B, since every magnetic field at every point, the magnetic field was B, and the angle, the common angle, the common thing between all the pair of vectors B and dA was that the angle between them was theta, and that angle can be used to represent the mismatch between the direction of A and B. So for such case, for such uniform regular cases, performing integration is not necessary. You can just directly evaluate the flux by doing the bigger dot product, which is B dot D, B dot A, where A is nothing but the total area vector, and total area vector is actually the magnitude of total area vector for this case. For the area enclosed by the loop will be just the area length times breadth, that is the magnitude. So for this case, the flux will look like B L small b, where L and small b are, small l and small b are the dimensions of the rectangle, times cos theta. So that's it. So you need to know B, the magnetic field, the uniform magnetic, the value of the uniform magnetic field, the length and breadth, which are the dimensions of the loop, as well as the orientation of B, magnetic field vector B, with respect to the area vector A, which is incorporated by the angle cos theta. Another example where we can analyze the magnetic flux is in the case of a circular loop. Let this circular loop be placed within a region of uniform magnetic field. So which means the magnetic field at every point within the circle C will be will have a constant value and will always will all point at the same direction. So just for the sake of representation, I am going to represent a few magnetic field vectors. In fact, all the points inside the circle has this magnetic field inside it. So just represent one vector. Okay, now you know the area vector of this circular region will be perpendicular to the surface, let it be, say, at for a given point, let it be dA, okay. Now we move on to analyze the tiny flux d phi, which is nothing but B dot dA, and we know B dot dA is nothing but B dA cos of the angle between them. Since it's a flat surface, all the dA's point in the same direction, and also since it's uniform field, all the B's also point in the same direction, which means all the angle between dA's and B will also be a common constant, which we can call it theta. So we get it this way. Two facts: B is constant, orientation is constant. Thus, while evaluating the total flux from the given tiny infinitesimal product, we can get the B and cos theta out of the integration, thus leaving us with only integrating the tiny areas, which means you will have to add the all tiny area values within the region, which will give you the total area of the region, which is nothing but area of the circle, and area of the circle will be, say, if r was the, if small r, or say let it be capital R, if capital R was the radius of the circle, then this product will be b cos theta pi r square. So that's the flux through a circular coil oriented at an angle theta with respect to the magnetic field, having placed in a uniform magnetic field having radius r. We can go ahead to evaluate magnetic flux using the general formula phi equal integral b dot dA in any complicated cases, but integration needs to be defined properly, and we need to know the limits under which we do the integration. If we know these three things, then evaluating the integration is just a matter of time. Now we move on to the concept of electromagnetic induction. Here we state the concept and the principle. The concept and the principle. So if you have a conductor like this, so this is a conducting material. I have or suppose we have just made a wire out of it. So how to make a coil out of it? Just wind the wire. So let me represent the wire using some other color. Okay, you have this wire. Now what you need to do to make it a coil? Just wrap around the wire like this. Okay, let this end be A, let this end be B. So representing them on the diagram, it looks like this. Okay, so that's your coil. This is the coil C, and this is the this much. Once again, let me just use a different pen. Yeah, this is the area enclosed by the coil. We need to know the flux associated with this coil. Now you know how to evaluate flux associated with a region. So if you know the total flux through this region, if you know the total magnetic flux through this region, see, you need to have a magnet, you need to place the coil in the presence of a magnetic field to have a magnetic flux associated with the coil. Suppose you are keeping the coil in the presence of a magnetic field and you somehow got to know the total magnetic flux associated with that coil. Okay, if you know that, you can now to evaluate the induced EMF and the induced current, all you need to know is how fast this quantity, this magnetic flux, how fast magnetic flux associated with the coil changes with respect to time, of course. So that's a very important point over here. You will have to know how this quantity phi changes with time t. So if you know this, you can evaluate, you can analyze the concept of electromagnetic induction. So what is electromagnetic induction? The idea or the phenomenon of electromagnetic induction is in fact induction of electricity, in fact its electric field to be proper, induction of electricity. What is induction? Induction is actually synonymous to production or generation or to produce. Okay, so induction of electricity, in fact it is electric field inside a coil or loop when magnetic flux through the coil changes, through the loop changes. Coil or loop can be used synonymously. Changes. So this is not a formal definition of electromagnetic induction. In fact, the formal definition of electromagnetic induction is a bit different. Let me state that next. So before going on to the formal statement, let me just give you the idea how you would state it. So if you have a coil, and if you have a region that encloses the coil A, then also this coil is placed in a magnetic field. Of course, there is magnetic field B in that in the region where you have placed the coil C. Then an EMF is induced, and an EMF is induced in the coil C, which means there is electric field. We will have tangential electric field to the coil. We'll have tangential electric field to the coil, which would drive the electrons or the free charges within the coil. Okay, you will have an EMF. In fact, EMF means you have a potential. You have a potential drop, which is actually there is this electric field thing happening. An electric field is induced at every point on this coil, and the electric field at every point on the coil will be tangential. So at every point on the coil you will have a tangential electric field induced. There will be an electric field at every point will start to appear when an EMF is induced in a coil C when magnetic flux associated with the coil changes. An EMF is induced in coil C when magnetic flux associated with the coil changes with respect to time. So this is one statement of electromagnetic induction. Another way in which this can be stated is in terms of electric field. This is in terms of the potential difference or the potential drops at each point. Instead of that, we can talk about electric field is induced. Field is induced at tangentially at each point of the loop when magnetic flux within the coil, within the loop, changes. So this can also be a restatement of the above given thing. So this both actually ultimately represent toward the single phenomenon known as the electromagnetic induction. This generation of electric field, this induction of EMF is actually potential drops at every point. So EMF or the electric field, all these are induced at, not all these, but actually electric field and EMF are related by the relation, by the equation V is equal to integral E dot path integral E dot dl. So in fact you can either say it is potential EMF or you can say it is electric field. Both are equivalent statements. So anyways, they point towards the same phenomena known as the electromagnetic induction. Electromagnetic induction. So this is the phenomenon of electromagnetic induction. So this is the concept. Now what is the principle? The principle behind electromagnetic induction is actually a mathematical restatement of the phenomena, where the amount of EMF induced which is represented by epsilon. So this is the amount of EMF induced or magnitude of EMF induced within the coil. See, when I say within the coil, it is actually along the path of the coil. Okay, so the EMF is induced along the path of the coil. So it is actually in here. It's this path of the coil along which the EMF is induced. So any charge on this path will experience an electromotive force which will drive them along a particular direction. So there will be a potential difference between A on this side and B on that side, which means this will be at this point. I mean, you cannot state it as two different points, but you have a point A, and on one side of that point it will be a higher potential, and on the other side it will be a lower potential. And what will happen to charges? Since it is the same point, you cannot distinguish between potentials within the point, but only you can experience the potential difference along this bigger path. So any charges at higher potential will positive charges obviously will start to move towards the lower potential. So this happens at every every point. So at every point this happens. It's not only at a particular point, but this happens at every point, which means all charges start to move along a loop, and this movement of charges constitutes to the induced current. Okay, so the EMF an EMF is induced at every point on the coil that drives every charges along the loop, along the path of the loop. And the principle of electromagnetic induction states that the amount of EMF induced is proportional to the rate of change of magnetic flux associated with that particular loop. So the amount of EMF induced in a coil is proportional to the rate of change of magnetic flux within the coil, through the coil, and it happens to be in a direction opposite to the polarity of the induced EMF is opposite to the direction in which the rate of change of flux happens, which means it's better I would explain this negative sign later, because we will have to understand another law to understand why this negative sign is here. But for meanwhile, just take it as such. We would explain this later. So anyways, the principle is this: the induced EMF within a coil is proportional to the rate of change of magnetic flux through the coil with respect to time. So the rate of change is measured with respect to time, and this is a derivative. This is a derivative quantity. It's the derivative of the magnetic flux with respect to time. If you have studied mathematics and calculus, you would know what these symbols represent and mean. All right. To get rid of the proportionality sign, we introduce a proportionality constant, say k. Don't forget to put the negative sign, it's very important. K minus k d phi by dt. But k was for definitive reasons assumed to be 1. Thus the units of epsilon and phi would have changed accordingly, giving us an equation epsilon equal to minus d phi by dt. This is how you quantitatively analyze the amount of EMF induced, and this mathematical restatement itself is known as the Faraday's law of electromagnetic induction. So what does this equation say? The physical meaning of this equation, the concept behind this equation is that it gives us the value of the induced EMF, To know the value of the induced EMF, we need to know how fast the flux through the coil changes. So induced EMF is actually equal to how fast magnetic flux changes. It also says that the amount of induced EMF is proportional to the fastness of the magnetic flux's change, which means if magnetic flux is changing faster, there is more EMF induced, and if the magnetic flux change is lower, less EMF is induced. So EMF is proportional. The EMF induced is proportional to the rate at which magnetic flux changes. So faster the change, more the EMF, lesser the change, smaller the EMF induced. So putting those equations into statement, we can state Faraday's law of electromagnetic induction as, so Faraday's law of electromagnetic induction Faraday's law of electromagnetic induction. So we are going to state the statement. We are going to write the statement. We can state the Faraday's law of electromagnetic induction in two parts. Part 1 would be, whenever a conductor need not be closed, okay, whenever a conductor need not be closed, is placed in a varying magnetic field, an EMF which stands for electromotive force. Electromotive force is not electromagnetic force, so it's electromotive force. An EMF is induced at each point of the conductor. And the second statement, the EMF induced in a coil placed in a varying magnetic field, is proportional to is proportional to the rate of change of magnetic flux within the coil. You can call it the flux linkage. Magnetic flux, you can either call it magnetic flux within the coil, or also you can just alternatively state it as change of magnetic flux linkage, which means it's just the magnetic flux linked with the coil. Okay, so you can also call it magnetic flux linkage. So this is the statement of Faraday's law of electromagnetic induction. Now what remains is the direction of the induced current to be analyzed. We now know the amount of EMF induced, but we do not know the direction in which the induced current flows. So to analyze that, we'll have to study another law which will give us the polarity of the induced EMF, or the direction in which the induced current should flow. And the law which states gives us the polarity, or gives us the idea about the polarity of the induced EMF, or the direction in which the induced current flows, goes by the name Lenz's law. Lenz's law is due to a Russian scientist known by the name Emil Lenz in the year 1834, during his formulation of the concepts of electrodynamics. So to understand Lenz's law, we will have to look at a few circumstances. First of all, let me assume a coil. So throughout my lecture I will be using circular coils, so please don't get your brains hardwired to circular coils alone. It can be coils of any form. It can be irregular shape, such as like this one. It could be a rectangle, it can be a square, it can be a pentagon, right? So always have this in mind. So for the sake of simplicity, I'm using circular coils. So let me call the coil C. Now, so I need to know the direction in which the induced current moves. So in this case, in this coil, there are only two directions in which the induced current can move. It can either move in this direction. So if you are front facing in this direction, that is anti-clockwise. No, that is clockwise if you are facing in this direction. And it could move in the opposite direction, which is, if this is the front facing direction, then that would be anti-clockwise. I think it's better I draw it in the flat screen direction. So suppose this is the coil and you are looking onto the coil, then the induced EMF, sorry, not the induced EMF, but the induced current will be either in the clockwise direction or in the anti-clockwise direction, right? That is the only possibility here. No other possibility, but the only possibility are these two. So how to know whether the induced current is moving in the clockwise or anti-clockwise direction in the for the observer who is facing the coil? Okay. For that, you need to understand, not understand, but you need to know the fact that the energy in the universe of isolated systems not just energy but total energy, you should also say total energy in the universe of isolated systems is always conserved. So this fundamental law known as the law of conservation of energy is always conserved, not conservation, is always conserved. This fundamental law known as the law of conservation of energy is what leads to the Lenz's law. So let us analyze the situation based on this conservation law. Okay, you know that the total energy of a universe should always be conserved. Okay, which there are other statements for the similar law. I mean, for the same law, there are other statements also, like energy can neither be created nor be destroyed. So that's one more statement which actually binds with the law of conservation of energy. Actually, law of conservation of energy can be stated in these two ways. Energy can neither be created nor be destroyed. And there is one more way in which you can understand or at least state the law of conservation of energy, and that statement is no machine can do work perpetually without external energy input. Perpetually, the term perpetually means forever, for infinity. You can never make a machine which will maintain its motion, or it can maintain producing work without an external input of energy. Suppose if you have a motor and you start running the motor, okay, just imagine if you have a motor, you somehow use a battery to run the motor. Okay, now when you run the motor, what happens? it rotates. Now you might imagine that this rotation can be used to rotate a dynamo, okay, a generator, an electricity generator. Now when electricity generator is working, it will produce electricity. Now why don't you use that electricity to run the motor again? So the motor will keep working, the generator will keep working, so these two together could end up being a perpetual machine, right? These two together can make up a perpetually moving machine, a working machine. But that does not happens, and that does not happens because of the law of conservation of energy. So how can we make use of law of conservation of energy to understand Lenz's law? So let us go into it. Imagine the coil. Imagine a coil. Okay, this is a metallic wire folded into a coil shape. Okay, a circular coil shape. Now take a magnet, a bar magnet with north pole facing this side of the coil, okay, and south pole away, facing away. To induce current in the coil, we'll have to quickly move the magnet either away from the coil or quickly move towards the coil. So whenever during the time when the magnet keeps moving, there will be a current in the coil. So let me just plot a graph to analyze the situation also. Okay, so this graph represents time, or at least time, or not time but location, place x, which means this is x, okay. Suppose this is A and this is B, which is, those are the 2 points at which these magnets are going to be placed, A and B, okay. So when between I pick up the magnet, okay. Then when I pick up the magnet, I start moving it from here to here. So the magnet moves from B to A. So when I move it from B to A, in between A and B, it's moving, okay. Here it is moving, it's moving from A to B, okay, or it's moving from A to B or B to A, either way. So let me keep it at B. Okay, now the magnet is at B. I move it from B to A. So within B and A, within the limit B and A, the magnet is moving. So whenever the magnet is moving towards the coil, the flux is changing. So within that, this y-axis represents the induced EMF, okay. So within that region, there will be an EMF. If you are moving it at a constant rate, there will be a constant EMF, okay. If you have a constant rate of change of flux, then there will be a constant EMF, say epsilon 0. But beyond that, when the magnet is has stopped, there is no EMF, okay, fine. So there is a burst of EMF in the coil. That EMF will induce a current, an induced current, okay, fine. Now let us see. So so as I have told you earlier, there are 2 directions in which the EMF the current induced could flow, either clockwise or anti-clockwise. So let us look at what happens when the current induced is clockwise. In this situation, okay, in this situation, let the current induced be in the clockwise direction, okay. If the current is in the clockwise direction, what will happen? when you bring the north pole from B, north pole side of the magnet from B to A, you assume that the current was clockwise. Okay, we are just assuming this. Okay, we are just assuming this. We do not know whether it is clockwise or anti-clockwise. We are just assuming it is clockwise. What will happen if it is clockwise? Let us see. You know, when there is a current in a coil, and if you know the direction of the current, using a right hand thumb rule, you can predict the polarity of the magnetic field on the facing side, right? In this case, when you apply the right hand thumb rule, you know that this side there will be the north pole of the magnetic field will be induced in this side. Okay. Oh no, sorry, I'm extremely sorry. That's not north pole, but there will be a south pole here. There will be south pole on this side. So when you are facing a coil and when the current in the coil is clockwise, there will be a south magnetic pole on that side of the coil, which means when you're bringing the north pole closer to the loop, if you see a clockwise current, that clockwise current would result to a south pole on the coil. What happens if south pole is induced here? You know, when you keep magnets with opposite poles facing each other, they will start attracting, they will start pulling each other, which means if you are keeping a north pole, if point B is at infinity, okay, suppose that point B is at infinity and your north pole is here, your south pole is here. Now you just push the magnet towards the coil. What happens? There will be an anti-clockwise current assumed. Okay, we have assumed that there will be a magnetic anti-clockwise current induced, and this clockwise current will give you a south pole on that facing side. Now what will happen? This south pole will now start attracting the north pole of this magnet. Okay, the south pole on the coil will start attracting the north pole on the magnet. Now this will result in an attraction, which means you have just tapped, and now the magnet is not moving by your force, but instead the coil itself is pulling it towards. The coil itself is pulling the magnet towards it, which means north pole is moving. When north pole is moving, there is a flux change in the coil. That flux change will produce more current, and that more current will produce a bigger south pole, a stronger south pole. This stronger south pole will pull the magnet even faster. This magnet will start to accelerate towards and towards and towards the coil from infinity, and all you have done is just tapped. What did you do? You just tap the magnet, and after which there is no external source acting between these two systems, but they are just pulling themselves closer together, which means you have produced a machine which keeps on moving forever. And that actually breaks the law of conservation of energy, right? There is no external input of energy, but still you can produce. Just imagine if you have a coil at infinite, like 10 million miles away. You have made a coil at a certain location, and you have a vehicle which has a north pole at the front face. Okay, now what happens if you just push this if you just push this magnet? What you are doing is you are actually changing the flux in the coil. That will produce a clockwise current, and that clockwise current will produce a south pole, and this south pole will attract north pole, and that attraction will pull your vehicle even faster and faster and faster. That means free of fuel, you are going towards that particular coil, which means you are traveling 10 million miles without even spending a single a single drop of fuel. And also suppose that there's a city over here, that city can also make use of some part of the electricity to drive their entire city, right? I mean, that too is a possibility, right? There is no input of energy anywhere here. All you just did was push this north pole of the magnet towards that coil, thus inducing a clockwise current. But that is impossible. That situation is totally impossible because there is this, because our universe obeys the law of conservation of energy, which means our assumption that there was a clockwise current was wrong. So when you bring a north pole of the bar magnet or of any magnetic source towards a coil, the facing side will never ever have a south pole, but instead it must have a north pole polarity. The coil, the facing side of the coil must have a north pole polarity, which means if it has a north pole polarity, then using the right hand thumb rule, the current in the coil must be anti-clockwise. Now what is the benefit of having a north pole? Just see, if you are pushing it, you are getting a north pole. What happens if north pole is induced? This north pole and the north pole induced in the coil both repel each other, which means you are to generate more and more electricity, you will have to externally apply force. So when you are applying force externally, which means you are working, which is you are inputting some energy into the system, and that energy is exactly what gets converted to electricity. So this is the law that the coil, the induced current must obey in order to preserve the law of conservation of energy. So that is how we state Lenz's law. So let us look into the Lenz's law. So Lenz's law is in par with law of conservation of energy. And what does Lenz's law states then? Now Lenz's law then states that the polarity of the induced EMF is such that it tends to produce a current, always emphasize, it tends to produce a current which opposes the change in magnetic flux that produced it. Okay, let us analyze the statement. Let us look at the previous example. See, if we bring a north pole towards a coil, we are bringing a north pole towards a coil. Okay, now you are bringing a north pole towards a coil. Now we know that the induced current should be such that there must be a north polarity here. I mean, it should not be south pole, but it should be a north pole. Now what does north pole do? When you are trying to push the magnet towards the coil, the magnet is trying to repel the magnet backwards, which means the change when you push, when you are pushing the magnet, so this is repelling when you are pushing. Okay, what are you doing by pushing? You are trying to change the magnetic flux, through the coil. Okay, you are trying to change the magnetic flux through the coil, but the coil is trying to repel you back, which means the coil is trying to prevent that change. Okay, prevent that change because it does not want to be changed. Okay, it's trying to prevent that change of flux. So how does it prevent? It prevents it by inducing a current in such a direction. Okay, in such a direction. So that's what it is doing. It's inducing a current in such a direction that would prevent the change in flux. That's what this statement is. That's what the entire statement is. Okay, that's what the entire statement is. So the polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. And this statement, this law, is in fact in accordance with the law of conservation of energy. So now you can easily analyze various situation. Let me just give you an example. Suppose you have a coil. Instead of north pole, I am bringing a south pole towards this coil. What will happen? What will happen at the coil? The coil will try to prevent the change in flux. What will it do? It will try to, when you are bringing it towards it, when you are bringing the south pole towards it, this coil will try to repel it. How will it repel it? This is south pole, which means it will induce a south pole here. Then according to the right hand thumb rule, the induced current must be clockwise. So it will induce a current which is clockwise. So when you push a south pole towards the coil will produce a clockwise current. So there you get it. You have generated a current which is clockwise. Now these two situations where in one case it was pushing a north pole of the magnet towards, you found that it was a north pole that was produced, and which to produce a north pole you will have to have an anti-clockwise current. Now you know these two situations very nicely. Now can you predict what happens when you have not pushing but instead you pull those magnets away from, when you pull those magnets away from the coil? Suppose you have south pole facing the coil. Now you are pulling the bar magnet or any magnetic source which has the south pole facing the coil away from it, and also you have this north pole. You pull that north pole away from the coil. What will be the direction of the induced current? Can you guess? If you want to guess, please pause the video and guess your answers, and then you can replay. Okay, you might have guessed your answers, but let me just explain the answer here. Now you are trying to pull the south pole away from the coil. Now you are pulling the south pole away means you are trying to change the magnetic flux linked with the coil. So you are trying to change the phi which was already there within the coil, and you are trying to change it. Change it means you are trying to change phi from phi prime. But what happens? Coil has this tendency not to change it. So not to change it. How will it not change? You are actually pulling away. Then the only way to stop it is to call it. Like, see, for example, if you have your boyfriend, okay, or girlfriend, and you were both at a location, you want your boyfriend or girlfriend not to go away from you. What will you do? You will call them, right? Which means you will start to do as much poses as possible to attract them. How can you attract a south pole? You can attract a south pole just by having a north pole on the facing side of the coil. That means if it is north pole here, then that must be anti-clockwise current. So when you pull a south pole away, the induced current will be anti-clockwise. So you understood this, then this is very easy, right? Just do the opposite. You are pulling north pole away. If you are pulling north pole away, you will have to stop it there, which means you will have to try to attract it. How will you attract it? You attract north pole by facing a south pole of the magnet, which means the coil will induce a south pole here. Then according to the right hand thumb rule, south pole is induced in the facing side if the current is clockwise. So in this case you have clockwise current. So all the situations have been closely analyzed.